talking about effective ways of solving some PDEs with complicated boundary conditions and unbounded domains.
Thank you very much. Thank you for the organizers for letting me speak, and thank you for the organizers to bring in this lovely cohort of people all together so we can have a bit of fun with complex analysis and numerical methods. So I will try to keep my talk as simple as possible and just kind of cover the range of different complex analysis numerical techniques that I've been playing with in the last so many years. And for the first part, which is going to be concentrating on the matrix Wiener-Hopf problems, my collaborator is Mathieu and Lorna here in Cambridge. And for the second part, another Mathieu, Colbrook, is going to talk about some Mathieu functions. So this is the plan. I will first introduce, in case you haven't seen what a Wiener-Hopf method is, and talk about two different ways of looking at the Wiener-Hopf method and how this can be computationally used, and then talk a bit about rational approximations, because I love rational approximations and chap fun. And also, I will, of course, a lot of people here do, so that's why it's a lovely place to talk about it. Anyway, then I'll talk about when can't we use rational approximations and what can we do instead of rational approximations. In some sense, it's a generalization of that, and I'll be talking about iterative methods. So instead of trying to solve a complicated n-by-n matrix problem, we're going to reduce it to much simpler scalar problems. And that's going to be linked with the new method, new software which is being developed for solving singular integral equations, and that's a very effective way of computing Cauchy-type integrals. And then briefly in the second half, I'm going to talk an entirely different approach to the same type of boundary value problems using special functions, and special functions are also very cool, in particular Mathieu functions. And that would allow us to solve using collocation type methods to very kind of complicated boundary conditions where you vary the porosity of the scattered field for the scattering and vary the elasticity. Anyway, but before I talk, I'm going to motivate it by saying, well, we had a Wiener-Hopf program, and this is the logo for it, and Shihan Olver has posed an open problem. So this is the room to pose it to. The kind of matrix Wiener-Hopf problems I'm going to introduce and solve in my iterative numerical method can't at the moment be solved using the Riemann-Hilbert solver which is available. So if you can adapt it and kind of find a different way, that would be very cool. I'll present the way I'm going to do them. So at the moment, we can't just find a software where we can plug this problem in and it will find an answer. So which kind of problems are we looking at? We're looking at what's called a Wiener-Hopf problem. So we have two functions which we don't know, a plus function and a minus function. And by plus function, I mean a function analytic in the upper half plane. A minus function is analytic in the lower half plane. There's some relationship between this plus and minus function which holds on a strip of the intersection between those two half planes. We know what this function is. We know what this function is, and they're very nice functions. Let's just say they're analytic in a strip around the real axis. So this is a very nice type of a Riemann-Hilbert problem. You get extra analyticity of this. The only real problem sometimes we get, well, we get it quite a lot in applications, is that our contour is the real line, and at infinity on this real line, we get some very nasty behavior. Anyway, just kind of recapping the standard way of doing this problem, the classical way, you would take this function here, and what you want to do, you want to write it as a multiplicative splitting or factorization into a plus and minus function. If you can do that, you can multiply through this equation, and then you're left with a term which looks like this. And again, you want to split it into something analytic in the lower half plane, analytic in the upper half plane. And why do you want to do that? It's because then we have an equation which looks like this. Everything on this side has pluses, everything on this side has minuses. That means that we can use analytic continuation, Liouville's theorem, if we have enough properties about the decay of this type of functions at infinity, and we can say that this is equal to, in general, a polynomial, and this is equal to a polynomial. So we have found a relation, we have found what this is in terms of those things which we know. Okay, so that's the classical Wiener-Hopf method. There's a different way of looking at this problem. So if we start again with the same equation, but now suppose that this A has a very specific form, in particular it's rational. Then what we want to do instead of finding a factorization of this, and the reason we don't want to find a factorization is even though in the scalar case we can find this factorization numerically quite well, in the matrix case we have no idea in general how to do it. So we want to try to avoid this factorization. What we can do instead, we can do additive splittings. We can do that for scalar, we can do it for matrix, it's fine. So we will try to do this. We'll try to do this. In the special case where this is rational, we can write down what kind of the general expression in terms of residues for that and for this, and then we end up with something which looks like that. And this is a linear system which we can then solve and find those coefficients. Okay. So that's very nice. So suppose we want to do that, but we don't have a rational function there. A very natural idea and something which has been exploited by a number of people, and David Abrahams made it very systematic, is to try to approximate this function by a rational function. So suppose we were given a nice function, and this is our nice function, which is just kind of has two branch cuts in the upper and the lower half plane. Looks very nice on the real line. We want to approximate it, and why do I want to approximate it on the whole real line? Well, I want to be able to say something about the errors in doing so. And if I want to say something about L2 errors in doing this approximation, I need to know that my approximation is valid on the whole strip. Okay, so this is a nice function. I want to approximate on the whole real line. How do I do that? I map this function to an interval. When I map it to an interval with a nice Mobius transformation together with a Jakovsky map, I get a very nice function. A function like that is very easy to approximate using Chapman. So here is your almost equilibrating error. And this is how the error looks on the whole real line. Note that for a very small degree we get very high resolution. And what's more important, that's where the complex analysis magic comes in, we have that the poles and zeros align perfectly, these 10 to the minus 7, almost perfectly where we expect the branch cut to be, and we have this intertwining, interlacing of poles and zeros, simulating what a branch cut might look like. So in fact, on the whole real, on the whole complex plane, this function is very well approximated. So this is very good and very nice, and it works for some problems. Unfortunately, it doesn't work for all problems you are interested in from the point of view of acoustics. In particular, if we have not just finite branch cuts but have infinite branch cuts, this doesn't work. So let's try to look at some other ways of doing it. So this is a motivating example. We just have an acoustic wave. We have two different boundary conditions. We have Neumann from here to infinity, and we have this finite length Robin type boundary condition. Helmholtz equation, we do the usual trick. So the way to get a Wiener-Hopf equation, you want to do, you're taking the Fourier transform, splitting into two parts, the plus and the minus part. We know the boundary conditions, so we know one of them. The second one is the unknown one. Skipping all the details, we get this matrix Wiener-Hopf equation. And this is the type of Wiener-Hopf equation we can't at the moment just solve using some kind of Riemann-Hilbert numerical solver, which is currently out there. There's two problems. One problem, we have this exponential functions, some oscillatory functions here. Second problem, we have this gamma function, and this gamma function has this square root singularity exactly with its infinite square cut. So we can't use rational approximations or anything like that. to be sure that we capture the whole real line. And we can't use the standard Liouville theorem either, because we have something which doesn't, which exponentially grows instead of decaying or polynomial growth. So we have to do something a bit more involved. In particular, we start doing the factorization process. So we try to construct this plus and minus function we had before, but we can only partially do it. We can get this function, which is a minus function, and note it also has the exponential, which decays in the lower half plane, and we can do this plus, which has the exponential, which decays in the so that's this lower half plane, this is upper half plane. So we've done this partial factorization. There's still some bits which we haven't caught. So there's still, we haven't solved the problem entirely. And now what we do, we're going to reduce it to almost solving the problem. So we're going to ignore some of the terms. In particular, we're going to look at this first line, ignoring this term, in essence. And then we're going to look at this line. And then we're going to use the solution we computed the previous time to plug it into here, and so on. So basically, we're going to be solving scalar Wiener-Hopf problems of a very nice type, where the integral, where the decay is decaying exponentially fast in the half planes we're looking at. Okay, there was nothing very special about that particular example. This method works for general matrices of this form. It reduces to these coupled equations, and again, you can see that this coupling, you have this exponential function. It used to be this exponential function causing problems, but in the way that it's posed here, it's in the right half plane, so it actually helps us. So this method, you'll see, converges fastest for high frequencies. So usually, the usual numerical problems you get for high oscillations, they become your friends rather than your enemies. Okay, and we can get explicit error bounds for those iterations, so that's very nice. This type of equations appear also from integral equations, and here is an example, and you can see how those iterations converge very fast to the true solution. So that's working very well, but we can also do that for more general class of problems. So not only 2 by 2 matrix functions, but if we have a more general scattering condition. So here we have 2 plates, and we have a same incident field on those 2 plates. This results, you have to take now Fourier transforms with respect to each of the ends of the plates. And again, you're going to get a matrix Wiener-Hopf problem. And now you again have those exponential functions on the off diagonal, and then you get this equation which encapsulates the behavior. Okay, so together with Mathieu Priddin, we have implemented that, and the difficulty here is then you're solving a lot of scalar Wiener-Hopf problems, so you want to solve them very fast. So here is another. So first of all, you have to rewrite it in a way that you can see there are some terms which are exponentially small in the right place. So that allows you to look at whatever scalar equation is relevant. You solve those equations, and then you iterate. So how do we solve those scalar Wiener-Hopf equations? Well, if you look at what's called the vanishing basis of Chebyshev polynomials, we have a function. We write it in terms of this sum, and then you consider those differences. Then there's a very nice relationship. I've not explained how, but a Cauchy type integral for our case reduces to an integral of this type, and then we can say that this is explicitly given by that. So that's the kind of the gist of what's happening. We're reducing an n by n matrix problem to a lot of scalar problems, and then we're using these Chebyshev polynomials, which is all implemented by Sheehan in Julia, and we can just compute them really fast. And this is the kind of pictures we get. So this is to be directly, this picture was produced to be directly compared with Hewitt's paper in 2000. as you've seen. And what I mean, there was a question how long things like that take, and in our case, on a normal computer, that's less than 6 minutes. So those algorithms, although they do many, many iterations, are extremely fast. You can vary whatever configuration you would like, and not only you get very fast convergence, you also get much faster convergence for higher frequencies. So you see, for very high frequencies, you only need very few iterations to get very high precision, but this works even for very low frequencies. You just have to have more iterations, but this is still practical.
That's 6 minutes of solve time or plot time?
This is just entirely to create this.
Okay.
Yeah.
You're evaluating that each pixel.
Yeah, yeah. So that's the whole computational cost, the whole computational time. And I've not said much. I'll talk a bit more about, but this is particularly good also. This is what's called the near field, but you can also do the far field computations very, very fast with those. And another feature of this is that it captures the singularities which you get at the edges of the plates very well. So there's a square root singularity, and that's inbuilt into the code. Okay, so that's one way of solving problems where you have a scattering on some kind of plates with complicated boundary conditions. If you remember, if you have this plate using a Wiener-Hopf method that result in a 2 by 2 problem, there's another way of thinking about it. You can think that a Fourier transform works very well for Cartesian coordinates. If you give me a problem and you give me boundary conditions on the whole real line, a Fourier transform will give you the solution. Well, if you now give me a boundary condition on an interval, then there is an elliptic coordinates which then give you the solution for this problem. So that's what they look like. So what's important about this picture is that we're given the boundary conditions on this interval, and we want to know what happens to the acoustic scattered field far away. So what those ellipses do, they kind of join what happens on a plate to what happens on the circle. Not going to go through too much details, but you can do a change of coordinates the usual way. You can do separation of variables. You get two equations, and you want to solve those equations, and you get funny looking functions. So this is what you kind of the analog of sine and cosine functions, and what's good about them is that you have these orthogonality conditions with those functions. And for the radial Mathieu functions, again you have an analog kind of a Bessel function, Hankel functions. And what's good about those functions is that you have far field asymptotic formulas available for them. So this is the plan. If you just had a rigid plate, you know you can expand the acoustic field in terms of those. What you do, you just put this in the boundary condition you have, and this comes out the solution. So this is the same thing you would do if you just have a Fourier boundary condition given on the whole real line. You do the Fourier transform, you put this boundary condition, and you get the exact solution. What we want to do is want to adapt it to more complicated boundary conditions. So instead of just having Neumann boundary conditions, we want to have very complicated boundary conditions. We no longer expect to get an answer of this type, but what we can do is we can still look for the solution in this form. We can still use the orthogonality, but we are reduced to a system which we then have to use collocation on. So this is the type of boundary conditions we can do. This can be more general. So on the plate, we have this kinematic boundary condition where we have a thin plate equation. What matters here, the only thing I want you to take out of here is that there's some parameter in terms of elasticity of this plate which we're going to vary, and that generally those kind of boundary conditions are quite complicated, and we have no hope of kind of solving those with methods, say, like Wiener-Hopf, because we want to now not have those conditions just as constants. We want to vary them across the plate. So we're varying the porosity, we're varying the elasticity across the plate. Okay, and this is the kind of plots you can get. So this is how I've chosen the elasticity to vary. So one of them is just a constant elasticity parameter. The other one is just a straight line. The other one is a sine. And what you can see is that at low frequency, this variation of elasticity doesn't make much difference. That's what we would expect. Again, there's not much difference here. Occasionally, when you get some kind of resonances, you can see that one of the profiles can give a much higher response. Now, the only thing which changed is that I've increased this value of elasticity, so now this variation is much higher. So you can see there's there's a shift happening in here in the direction. There's some kind of resonance happening here, and for this sine, you would see that this sine variation makes the structure more kind of responsive at higher frequencies, and you can see that there's more waves being reflected the other way here. Anyway, this is a fun code which will be Matt Colbrook wrote this, and he makes all his codes available, so this should be soon available for everyone to play around. And what's good about it, it compares very favorably with the current boundary element methods which are available. So this might not look very good. If you can see, so this is 10 to the minus 8, and this is 10 to the minus 3. So there's a massive difference in terms of if you have the same number of degrees of freedom, how many digits of precision you can get using the Mathieu functions and just using the boundary element method, and it's just much faster. So again, if you have to produce the full scattering plot for very complicated, it will be a matter of minutes rather than anything else. So I mean, the message is very straightforward. If you use the right expansions and the right analytical behavior first, and then do the computational methods, you get much faster methods. In the case of Wiener-Hopf, there's two ways of doing it. You can either exploit the rational approximation, or you can kind of exploit the fact that we can solve a scalar problem. For the Mathieu function, this allows us to solve kind of very complicated boundary conditions with varying elasticity and porosity. There's slight difference in terms of what you can do with either method. So Mathieu function is restricted to having just one interval. With the first method I presented, you can do multiple intervals as you like. And also, the Wiener-Hopf method is particularly good at a high frequency. And the Mathieu function, although both of those methods work across the frequency range, is particularly good at low frequency. But both of them are very much suited for finding the far field directivity, and that's something that kind of just doing brute force calculation might be difficult. And we've compared all those methods with the current numerical methods, and they compare very favorably. Okay, so just quickly at the end, if you know any good potential PhD students, I have an opening, please direct them. If you know any good postdocs, I have an opening, please direct them. If you're just interested in applying for any kind of research grant fellowship in Manchester, I'm very much interested and happy to help. Okay, thank you. No, because there's two things. There's first the number of iterations required to have the precision, and secondly is the complexity of computing the Cauchy integral for each of those iterations. So we haven't actually. So Mathieu Priddin, is he here? Yes. So he's the one who's done all the code for that. I don't think, correct me if I'm wrong, there is a particular simple formula for it. It's more or less frequency independent. Matthew, do you have a comment?